Hello, this is Mattia Sormani, and today I would like to talk to you about fueling the central regions of barred galaxies. So what is a barred galaxy? Well, in fact, barred galaxies are very common in the universe. For example, approximately 60% of spiral galaxies in the local universe are in fact barred galaxies. Let's see a few examples. Here on the left I show a barred galaxy from the PHANGS-JWST survey of Lee et al. And on the right I show an unbarred galaxy observed in the same survey. And on the left you see this elongated structure here, which has the shape of a cigar lying in the plane of the galaxy. And on the right instead you don't see such a structure. You see a more or less spiral that goes down to the very center. So this cigar-shaped structure is the bar. Here is another example. On the left we have a barred galaxy. Here I highlight the bar. You can see again this cigar shape. And surrounding it you see the spiral arms. And on the right instead you see something which is more axisymmetric and remains axisymmetric down to the center. Okay. What are bars made of? Most of the mass of bars is in old stars. And you can see the old stars if you observe in the near infrared. Here I show an example for the galaxy NGC 1300 observed with Hawk 1 at VLT. And you see all this diffuse light is made by billions of stars which are not resolved, so it looks diffuse. If we could resolve them, we would see many tiny points that altogether make the bar. And the figure of the bar actually rotates in the plane of the galaxy, but the stars inside it rotate faster than the shape of the bar itself. So it's a little bit like a swarm of bees that rotate faster than the bar, and then the whole swarm moves, in this case rotates as a whole, but slower than the stars or the bees that compose it. Okay, a smaller proportion of the mass is instead in gas and young stars. So here is the same picture from the same survey that I showed before, NGC 1300 from PHANGS-JWST, and the orange material that you see here is mostly dust and gas. If you observe instead in the optical, you can see more clearly the young stars. So here is the same galaxy with the Hubble Space Telescope, and all the blue material here are in fact young stars that are born from the gas that we have seen here in the previous slide. Okay, why are bars important? One of the reasons is that bars are able to channel large quantities of gas from the galactic disk on kiloparsec, so thousands of light years of distance from the center, down to hundreds of light years, so hundreds of parsecs from the center. And this happens, this transport of gas, through what are essentially two gigantic galactic rivers of gas. These rivers are shown here with the orange arrows. And this gas, once it arrives in the center, it can fuel star formation in the center, so the formation of new stars, galactic outflows, because all this star formation releases energy which can be ejected perpendicularly to the plane of the galaxy, and it can also constitute fuel for the supermassive black holes that are at the very center of all these barred galaxies. Let's see a movie from a simulation to illustrate better this concept. You see the bar here is always horizontal in this movie, and you can see these two rivers symmetrical on both sides, and you can see the gas in these two rivers that is flowing to the center and then accumulates in this ring where it will be able to do star formation and to produce the other effects that we just discussed. So in the movie you can clearly follow the individual molecular clouds made of interstellar medium that flow down this river. How can we derive from observations the amount of mass that is flowing to the center of these barred galaxies? PHANGS-ALMA CO survey opened up new possibilities to derive inflow rates in barred galaxies. In this survey, we measured the CO intensity of tens of these barred galaxies, and the CO intensity, so the CO is one of the components of the interstellar medium, and it can be converted into a gas mass. But we don't only measure the intensity of the CO, we can also measure its line of sight velocity through the Doppler effect. And by combining these two pieces of information, we were able to do a geometrical deprojection of these and find the flow rate along these two rivers, giant galactic rivers, that in the literature, in astronomical literature, are called bar lanes or bar dust lanes. The inflow rate will be simply given by the by the velocity of the gas along these bar lanes times the density, the mass density of them. Here is what the results that we get, for example, for NGC 1097, one of the most prominent nearby barred galaxy. And on the x-axis we have the future time, because we observe the river now, but the gas that is in these rivers in the current moment will reach the center of the galaxy in a few millions of years. So this is a prediction for the mass inflow rate that will be present at the center of this galaxy in the next 50 millions of years. And what we find is that on average the center, so the nucleus, the nuclear ring, gets a time average inflow rate of about 3 solar masses per year, and of these about 2 solar masses per year, so 60%, is currently consumed to form new stars. And in fact this galaxy shows a lot of star formation, so a lot of blue stars in the optical in this central ring. And the rest might be temporarily accumulated in the center, or it might be ejected as an outflow above and below the galactic plane, powered by the energy release of all these new formed stars. So in summary, in the PHANGS collaboration, we have developed a new methodology that uses the PHANGS-ALMA spectral line CO survey to derive the mass inflow rates in barred galaxies. For NGC 1097, we find an inflow rate of 3 plus or minus 2 solar mass per year when averaged over timescales of roughly 40 millions of years. And the next steps will be to apply these to more barred galaxies and to correlate the inflow rates with the star formation rates in a systematic way for a large sample of galaxies. Thank you.